This is an example of vector addition using the component method. We're going to add two vectors, they're velocity vectors, 24 meters per second at 25 degrees north of east and 42 meters per second at 31 degrees south of east. We're looking for the vector sum a plus b. The first step in the process is to sketch a diagram of a plus b using the head to tail method. You don't have to worry about being perfectly to scale, but you do want to have some rough idea of where your graph is going to end up. So we start with a coordinate axis and draw in vector A. From the head of vector A, we draw in vector B. I've estimated these angles and the measurements, but I've made B longer to represent the fact that it's a larger value than the vector for A. The resultant vector is from the tail of A to the head of B. So we want to draw that in there as well. The next thing you want to do is sketch in your components of each vector. The x and y components can be drawn in either order, so you can either do x and then y or y and then x. We'll label these ax and ay. And what we've just done is made a right triangle with vector A as the hypotenuse. Now we'll do the same thing with vector B. Ultimately, when we add the two x vectors together, it will equal the x component of the resultant vector. So ax plus bx will equal a plus bx. And then we'll do the same thing with the y vectors. ay plus by is going to equal the y component of our resultant vector. What we're going to do next is create a table where we calculate each vector's x and y components. We'll start with vector A, and we'll start with the x component of vector A. Now keep in mind that sine of theta is equal to opposite over the hypotenuse, and cosine of theta is equal to the adjacent over the hypotenuse. So when we look at the angle that we know here, we have this angle indirectly. From the x-axis, we have 25 degrees. So this angle right here is not 25 degrees, but rather 90 minus 25 degrees, which is 65 degrees. So we're going to look at, since we drew the y component first and then the x, we're going to work with this 65 degree angle. Had we gone over and then up, we'd be working with the 25 degree angle. So your diagram's very important in terms of how you evaluate this vector. Our x component is opposite our 65 degree angle, so we're going to use the sine function. If we're looking to find the opposite side, we would multiply the hypotenuse by the sine of theta. Our hypotenuse is a, so we're going to have a times the sine of theta, our 65 degree angle. So we go ahead and put in our 24 meters per second times the sine of 65 degrees, and we calculate that. Now we'll look at finding the y component, which is adjacent to our 65 degree angle, so we'll use the cosine function. Ay is what we're looking for, which is the adjacent side of our triangle, so we'll multiply the hypotenuse by the cosine of theta. The hypotenuse of this triangle is a. So we have a times the cosine of theta, or 24 meters per second times the cosine of 65 degrees. Notice that had you used the 25 degree angle, you would have had 24 times the cosine of 25, which also gives you 21.8. You would have had, for the y component, 24 times the sine of 25, which gives you 10.1. I am leaving one extra decimal point here, or one extra decimal place. We'll round at the end for significant figures. We'll do the same thing now for the second vector. This time we'll be using this angle that's adjacent to the x component. So when we look for b sub x, which is the adjacent side of this triangle, we're going to work with the cosine function. B, which is the hypotenuse, times the cosine of theta will give you b sub x. And calculating that, we get 36.0 meters per second. And we move to the y component. The y component is opposite of our angle. So we're going to use the sine function. B times the sine of theta, which translates to the hypotenuse times the sine of theta, is going to give us our opposite side. So we have 42 meters per second times the sine of 31. Now that we have the individual components determined, we have to double check our signs. We look to see if any of these vectors in our diagram are pointed to the left or down. If they're to the left, they're negative x components. If they're down, they're negative y components. We do have one of those. B sub y is in the negative direction, so we make sure that we put that negative sign there with b sub y. The next step that we're going to do is to add our x components together. Ax plus bx will equal the resultant's x component, and then we'll add the y's together. Ay plus by will equal the resultant's y components. You can see that I've done that here. We're calling our sum, our resultant vector is c. So the resultant vector is x component we found by adding those two x values, and then we'll do the same for the y direction. Now that we have these two values, we'll draw a sketch of our resultant vector. We'll put our x component based on our cx value, and our y component based on our cy value, which is negative in this case, so it points down. With those two components drawn, we can see that we have a right triangle with vector c as the hypotenuse. Vector c should resemble our initial diagram, which had vector c going down and to the right as well. The sketch might not look identical because, again, they're sketches. But now that we have this right triangle with the sides figured out, we can use the Pythagorean theorem to determine our final result. Notice that I have, at this step, rounded to correct sig figs. We're not quite finished because since this is a vector, we need both size and direction. So we want to find the angle that the resultant makes with the horizontal. So the angle we're going to look for is this one. To do that, we'll use the inverse tangent function. Theta will equal the inverse tangent of the opposite side, which is cy, over the adjacent side, which is cx. Don't make the assumption that the opposite side is always the y component. It does depend on your diagram. In this case, we have 11.5 meters per second and 57.8 meters per second. Notice I have not put the negative with the 11.5. And the reason why we're going to do that is because we just want the size of this angle, and then we'll determine what quadrant it is and go from there to report our angle. So if we do that inverse tangent, we get 11 degrees. And looking at the diagram, here's east, we're going south of that. So this is 11 degrees south of east. There's other ways you can report this as well. If you found this angle right here, it would be 90 minus 11. So we would have 79 degrees east of south would be the other option. Our final answer here, 59 meters per second, 11 degrees south of east.